So, this is a first lecture on trigonometry and spherical trigonometry in Indian works. So, this is the outline. So, where I will first deal with the crucial role of trigonometry in astronomy problems, then Indian sines, cosines, that is Bhuja-Jya and Koti-Jya, and sine tables, some interpolation formula which are needed for finding the sine and cosine at an arbitrary angle, then determination of the exact values of the 24-hour sines, and Bhaskara's, some aspects of Bhaskara's Jyotpatti will be discussed in this lecture and the rest later. There is inevitably there will be some overlap between this lecture and the previous lecture. Okay. Now, the ancients had observed regularity in the motion of celestial bodies. So, by celestial bodies I mean stars, sun, moon and planets in the sky. And actually in the very olden days when things were uncertain, far more uncertain, and life was more difficult, in fact this is the only regular thing which they would have seen, one of the most regular things would have been the motion of sun and moon, and to a little far lesser extent the planets. The stars themselves have an extremely regular motion. That is, what I am trying to say is the following. So, you observe the motion of celestial bodies in the sky, okay, the so called celestial sphere, see what you see, and we see that the objects, all objects will rise in the eastern portion of the sky. So, then rise up, go to the top and then come down, okay, and all of them it will be seen that they will be moving parallel to what is known as a celestial equator, which is parallel to your terrestrial equator itself. So, all the objects will be moving from eastern portion of the sky, rise and go up and then come down, okay. That is what we see, everybody would have seen that. So, now this is the daily motion, okay, but apart from the one, what one has to see is the relative motion. If you see the stars, okay, if you see the stars, if you observe the motion of stars, the relative positions of stars will be always fixed. Relative positions of the stars will be fixed completely. Of course, now modern astronomy says that that also has a little bit of motion, but we ignore that. The relative positions of stars in the sky will be fixed. Of course, they are moving, but the relative positions I am saying. Okay. But whereas sun, moon and other objects seem to be moving in the background of stars, in the background of stars, in the sky. Suppose you trace a path, they will be moving in the background of the stars, and that will be from west to east. So, eastward motion. So, that is what is I am considering as the motion of these objects. Okay. Stars are extremely regular in the sense that if you see some star in the top portion of the sky at the night, let us say 12 o'clock in the night. So, next day it will be exactly in the same position about 4 minutes earlier. Similarly, the second next day it will be about same position about 8 minutes earlier, and so on, you see, and always it will complete one in the circle in this thing sky. I mean, if you observe the positions at some fixed time in the night, and then again so that is regularity, no question, extreme regularity will be there, and that period is, as it is slightly 4 minutes less than the day. So, 23 hours 56 minutes, that is called a sidereal day or the Nakshatrika Dina. The sun, moon and all that will be moving in the background of the stars, okay. So, that motion will be not so regular, not completely, and departures from complete regularity have been observed over millennia, okay, not centuries, millennia, okay, thousands of years. Ancient, by ancients I mean not only in India, Babylonians, Egyptians, okay, Greeks, so many Chinese, all of them have observed this at whatever level and whatever level of sophistication. Of course, earlier there was not much of mathematical formulation, only about for the past 2000 or 2500 years we have some mathematical formulation. Okay. So, now ancient considered sun and moon also as planets, okay. Whatever is moving, it is moving around the earth, from the earth you are seeing. So, they also are moving, so they are considered as planets. And what was seen was that over, that is why I said millennia, for a long, after long, the observations over very long periods, they found that the motion is not so uniform, with different varying degrees of non uniformity. For instance, sun itself is fairly more uniform, with some small departure from uniformity, okay. So, that is if sun, that we also in Indian terminology we say which zodiacal sign it occupies, you see, Mesha Rashi, Vrishabha Rashi, or that is zodiacal sign, okay. So, it will complete one revolution. First they thought it was 360 days, okay, it will complete, it will take 360 days. Then more accurate observations told them that it is 365 days, and some 366, and more accurate things, even 3000, 4000 years back it was known that it is not 365 but 365 and a quarter, see. So, that is the thing, and of course later some a few thousand years more they found that also is not accurate, but slightly less than 265, 365.25, okay. So, even in that it is not fully uniform, but slight departure for uniformity is there, but that is small. For moon it is even somewhat more irregular, okay. If you see the relative motion of the sun and the moon, okay, so that is, suppose this from let us say new moon day is when sun and moon are in conjunction. So, you take the observation from one new moon day to another, that is called a month, that is the masa or the month, okay. So, that the average is about 29.5 days, 29.5309 days, but that varies. Sometimes the motion may be the month may be just 28 days, and sometimes it may be 30 kind of a thing. So, there is a variation of about 2.5. So, that is because moon's motion is not that uniform, far more less uniform than sun's, okay. Now, planets, they do not have such an important role in various religious activities and all that, also they are not so conspicuous, but even then planets also they could see the regularities, but it is of a different nature, In fact, it is very difficult to see a pattern if you just observe, start observing, okay, sun, moon and all that. Suppose a person has a very good, extremely intelligent mind and he is very meticulous observation, he can find a pattern between sun and moon, their motion, planetary motion, their rate of motion and so on. But for planets it will be very difficult to guess, what is the kind of a thing. We know the reason now, that they move around the sun, whereas we are observing around the earth. But anyway, still they could make out that that there was some kind of a regularity in the this thing, motion, and there was non-uniformity. So, this non-uniform motion of planets, you see, that is at the crux of lot of developments in astronomy, okay, non-uniform, you see, how they handle the non-uniform, you see, and astronomy was the exact science in the earlier times, you see, before 15th century. So, astronomy played the same role as physics in the recent times, physics is some kind of a central science, you see, around which most fundamental of the science, around which other things are built. So, astronomy had a similar role earlier, okay, and then to explain this new non-uniform motion, trigonometry is required. That is what I am giving this background. So, trigonometry is needed to explain the non-uniform motion of planets. So, this was the historical context for developing trigonometry both in Indian and Greek astronomy. Okay. Now, we know, I mean, of course, even a schoolboy, a schoolgirl will know that the planets move in elliptical orbits around the sun, and moon moves in an elliptical orbit around the earth, and in a geocentric framework one can say that the sun moves in an elliptical orbit around the earth. You see, those orbits you do not observe, what you see is variations, it is in the background of stars, okay, and you have to construct the picture after observation over so many these things. So, behind the simple sentence that it moves in an elliptical orbit, there is extreme hard work over millennia. Now, the ellipticity will mean that there is some kind of a eccentricity, it is a departure from circularity, and that will lead to non-uniform motion. So, how was this taken into account in ancient astronomy? We have to see that. So, one had an so-called epicycle model for the motion of a planet, both in Indian and Greek astronomy. The details are different, but the basic idea is as follows. Okay. So, essentially, suppose you assume that to the first approximation the planet is moving uniformly around the earth, okay, in the background of stars. Okay. So, P0 is the so called mean planet or the Madhyama Graha. Okay. So, this is moving at a uniform rate in a circle called Kaksha Vrutta, called different. Now, this gamma, this is a reference line, is the direction of the first point of Mesha Rashi according to Indian, normally according to Indian convention. You would have, all of you would have heard of Mesha, Vrishabha and all that. So, that is a division of the zodiac, 127th part of this thing. The beginning point of that is the Mesha Adi, they say Mesha Rashi. So, now with respect to that you measure this angle, okay. Incidentally, only you observe the angles only, you all distance measurements came out later. You see, when you see some object, you see essentially the angle with respect to certain directions. So, this theta 0, that is called the mean planet, okay, which is moving uniformly. Okay. So, now to take into account the non-uniformity, you draw a circle of radius small r around P0. Okay. So, around this mean planet you draw a small circle. So, this is called a epicycle or Mandavruta. So, this is epicycle, okay, and this has a radius r, and there is what is known as an apogee, or we are called Mandocha in Indian terminology. So, this the direction of apogee, and how we get it, that is a different matter. You see, that we have to discuss. Just assume that there is some kind of apogee and there is a direction associated with it. Now, draw a line parallel to this direction of apogee and let it hit the circle at capital P. So, this is the true position of the planet. Okay. So, you got the point. This is P0 is the mean planet called Madhyama Graha, and P is the true planet called the Sputak Graha. Okay. So, now you have to find this. So, difference between them is P0 OP, that is the difference between the Madhyama Graha and Sputak Graha, or the correction you have to apply to the mean planet to get the true planet. Okay. So, P this thing, and that is where one can, true longitude is this theta 0 minus delta theta. I am calling this as delta theta, this small correction. Okay. And from the geometry, okay, you can refer to it later. See, you draw a perpendicular from P to the line extended from OP0 onwards. This PQO is 90 degrees. I mean, it may not look like this in the figure, but it is that. And then simple geometry will tell you that one can show that this delta, suppose this is K, OP is K, this is delta theta. So, then one can show that this delta theta is sine inverse or sine delta theta, or K sine delta theta is equal to R sine M. M is so called Manda Kendra. So, which is this angle between the Madhyama Graha or mean planet and the apogee. So, your delta theta, the correction will be sine inverse R by K sine theta 0 minus A, where A is the angle corresponding to the apogee. Okay. I mean, this of course you can look at it at leisure sometime. What I am trying to say is that this, so to know the correction delta theta, one needs the sine function. That is the important thing, you see. Details you do not bother now. So, to know the correction, you have to know the sine function. You should know how to find the inverse sine function also, sine inverse is there. So, that is to find the arc from the sine. So, this is how the trigonometric functions enter astronomy. So, thus to find delta theta for any theta 0 around you, A, we should know sine theta 0 minus A sine M, either by explicit construction or tabulated value. Okay. So, this is how it comes there. So, I mean, many of the developments in astronomy like this are intimately, mathematics in the earlier days are intimately associated with developments in astronomy. So, non-uniform motion, you are you have to know science and all that, so you have to develop a trigonometry. I mean, even to describe the circle and all that, you see, why do you say 360 degrees? Because earlier it was thought that the average year is about 360 days. So that is how, So no, it is not surprising that all the important works in important ideas in mathematics in the earlier days in India from Aryabhata onwards. So they were always in astronomy text. You see, mathematics was a part of the astronomy text, and later only Ganita Sara Sangraha onwards you will have independent treatises on mathematics. I mean, that is true even in the other western countries also, I mean the Greco-European tradition also. So they were intimately related, and many important developments in mathematics always occurred in relation to astronomy problems, like instantaneous velocity of moon, Tatkalika Gati, which was mentioned earlier. So that is what is needed in this thing, and that is the instantaneous velocity, intimately related to the development of calculus. Okay. But we are bothering only about trigonometry here. So similarly, to find the time from the shadow of a gnomon, okay. Suppose this is some Shanku, pillar whose shadow we are observing, and this is the vertical direction, and suppose the sun's rays are coming at an angle z. So then you can easily see that the shadow S is g tan z sin z by cos z. So clearly the trigonometric functions are coming. So this is a shadow, and then to find the shadow of time from shadows, that also was mentioned, one has to use so called spherical trigonometry, which I will discuss later. So actually this is the formula which is relating the shadow, I mean this angle z and the time h. Essentially h is related to the time, okay, it is called hour angle. So you can see that they are all related. So you can find out h from z if you know phi and delta also. Phi is the latitude of the place, delta is the so called declination. So determination of sine and cosine functions very critical to for time related things also, daily motion, okay. So as important a thing as time. So hence the trigonometry, critical criticality of trigonometry for astronomical calculations. So now we will discuss the Indian Jya. Of course, some of them have been done earlier, but let me repeat it for completeness. So this here you have a circle, okay, with the radius capital R, okay, and then this is your angle theta, and AB is the perpendicular like this, okay. So then AB is called a Jya, okay. The radius R is taken to be 21,600 minutes divided by 2 pi, that is nearly 3438. You have already come across this. So essentially you are taking the length of the circumference to be 21,600, which is the number of minutes in a circle, 360 into 60. The radius of that circle is Jya, Trijya, which is nearly 3438. So this is Trijya, okay. So then this r sin theta, that is the Jya, Indian Jya is r sin theta. So it is a length, that is the length, okay, and this OB is called the Kotijya or Kojya, and this BD is r into 1 minus cos theta is called Utkamajya or Shara, and this also has been discussed, okay. So this is how it is. Of course earlier it was called this, I will come to that. Yeah. So now the Greeks worked with chords and Indians with r sines, okay. Suppose this is a relation, see, suppose you have a circle like this, okay. So this is the angle theta, so AB is the Indian sine or sine theta, whereas chord, so this is does not touch the circle, right, it is only half of this chord is AB and chord is AC, right. So AC is chord of the angle 2 theta, which is 2AB, which is 2r sin theta, okay. So Greeks work mainly with the chords and Indians with the sines, all, in fact only exclusively with sines after Aryabhata, okay. And of course earlier India also this used to be called Jya, and then AB was called Jyardha, okay, but later that was given up and this itself was called Jya, okay. Now the important thing is the Indian sign is perfectly suited for writing formulae and performing calculations. If you actually want to go through that, I wrote that figure, you have to calculate the correction and all that, it is always the sine function which comes, okay. So the sine function, so then if you know the formula and you can write it easily in terms of the signs, not with chords. So, in always in Indian text there will be some formulae for calculating the positions of planets, sun, moon and planets. Okay. It will all can be summarized with some parameters and all that with some 2 pages you can summarize all the calculations. Okay. And of course, they will tell how to compute sine and all that, that is a different matter. Whereas in the Greek this thing, if you go to some work by Ptolemy, it is difficult to find out how to calculate. So, you will take you take this chord and then you go to the table and then find out this and so on and so forth. I mean, it is as accurate as the Indian thing, I am not denying that, but it is more difficult for computation, and Indians always enthusiastic about computation. You should have a quick picture of this thing. Okay. So, the full theory, the philosophical and all that can wait a little. So, because for this computational purposes this is most eminently suited and ideal actually. Okay. So, this is the Indian sine, and actually the very term sine cosine can be traced to India. See, Jya was also called Jiva, okay, and this was adapted by the Arabs, and when it went to Arabs around 6th 7th century, Jiba also it became. In Arabic is read as Jaib. Okay. So, Jiba did not mean anything, Jaib means some pocket or fold in Arabic. So, they started using Jaib, okay, which means pocket or fold, and it translated into Latin it is sinus. Okay. This meaning this got translated into Latin, then it became sinus, and from sinus you became sine. Okay. So, Jiva to sine, though they sound different. So, the term sine is derived from Indian Jiva. So, in India the complement of the Jya is Koti Jya. Okay. So, that is we have already seen that the complement of that you see. So, this is AB, if AB is sine, OB is cosine, right. So, there is actually sine of 90 minus theta, it can be viewed like that also. So, they always use Koti Jya or Kojya in short. So, some complement of sine is cosine. So, the sine and cosine are very much to do with India, just like algorithm, you see, it was mentioned earlier, it had to do with Al-Khwarizmi, who was interested in Indian ways of calculation. Okay. Now, 24-volt division of the quadrant to find out the signs, okay, that I will not you have come across this earlier also, maybe I should not go into details. So, you to find out the sine at any particular for any angle, you first find out the sines corresponding to multiples of 3 degree 45 minutes or 3 and 3/4 degree, which is 90 by 24. Okay. So, you find that out, and then sine tables and all that much has been said about it, but I just briefly summarize for completeness. So, this is the difference equation, second order difference equation for finding r sin alpha, I alpha. Okay. Second order difference equation. So, this is what was used by Aryabhatta, right. Even in the previous lecture you had this. So, I am not going to detail. So, first sin alpha, r sin alpha is r alpha is 225, it is given in Aryabhatta. Next is r sin 2 alpha is 449. See, all those things I need not explain, but a very crucial thing is that that this is a second order difference equation, and in the it is essentially equivalent of the second order differential equation d squared by dx squared sin x is equal to minus sin x. Okay. So, this is a very, and for that time at the time of this is in 499, it is a very important thing and remarkable. You see, there is one Professor Mumford, who is a Fields medalist, okay, very important, equivalent of Nobel Prize in mathematics. He had come to Chennai about 5 years back or so. So, he was really, there are some lectures on history of mathematics, and he was also talking about it. He was marveling at this fact that Aryabhatta had something close to that kind of advanced, and this is the most optimal way of generating a sine table. So, that is what was emphasized by many people, you see. So, from this the second order difference equation you can generate the whole thing, and the most cleverest way of doing things, and that is very important. So, I will not go into details of that. The exact second order finite difference equation is this. So, cos 1 minus alpha in the even the previous lecture you saw that. So, Aryabhata's values were slightly inaccurate. So, improved by Nilakanta. Okay. So, and the first sine he took as 224 minutes, sorry, this must be 50 seconds, 24 minutes 50 seconds are 224 plus 50 by 60, and these are the better approximation. Sin alpha is equal to alpha minus alpha cubed by factorial 3. Okay. And similarly, this was is 2 in 1 minus cos alpha, this was approximately 1 over 233 and a half, which is this. So, obviously, Nilakanta gets a much better sine table. So, you already listened to this sine table, no. So, this is how it is done, and please remember again that the Indian sine, okay. So, you have to divide essentially by 3438 to get the modern value of the sine. So, that is all. So, when they say sine, it is or sin theta, right. So, that is the Jya, and or is very close to 3438. So, that is what you have to remember. Okay. Now, how to get for an intermediate angle, how do we handle the situation? Okay. So, this gives only the sines at regular intervals of 3 degree 45 minutes. So, that yeah. So, for that you do the interpolation. So, r sin theta, the first is the first order interpolation. Okay. So, suppose theta is there, it is close to theta I, let us say. So, then r of theta minus theta I into, so by the rule of proportionality. So, what is done here is suppose that is, if theta I, if you are finding the r sin theta for theta I and theta I plus 1. So, this is the difference. Okay. So, for a difference corresponding to theta I plus 1 and theta I, this is the actual difference between the sines. And what is the value, what is the correction for an arbitrary difference theta minus theta I. So, by the rule of proportionality, so if this is the change for this change in the angle, what is the change of sign for this change in this angle? So, that is this. Okay. By proportionality you get this. So, what I am trying to say is that suppose you want to find this r sin at 300 minutes. So, the first approximation is that r sin 300 minutes. So, close to that is r sin 275 minutes, okay, plus 300 minus 275, okay, and r sin 450 or 550, right, 275, sorry, I am sorry, 225, this must be 225, yeah, 450 minus r sin divided by 225. So, this is the, and these are tabulated, right, 225 for 50 no. So, these are tabulated values. So, you have to, so for a difference of 225, this is the sign of sign difference, this is what you have to add. For a difference of 300 minus 225, you have to add this by rule of proportionality. Suppose this assumes that is linearly varying in that interval, which is not true. So, one should have a more clear, better approximation to take into account the fact that sine is not varying so uniformly, it is not a linear function, okay, to take that into account. So, the second order interpolation due to Brahmagupta. So, he says in his other famous work Khandakadyaka, Gatabhogya Khandakantara Dara Vikala Ghata Shatair Navabihi Aptaya Tad Yutidalam Yutonam Bhogyad Unadikam Bhogyam. So, multiply the residual arc left after division by 900 by half the difference of the tabular difference passed over, and that to be passed over, and divide by 900. By the result, increase or decrease as the case may be, half the sum of the same two tabular difference. The result which less or greater than the with it should be difference to be passed is a true tabular difference to be passed over. This is the mechanical translation. So, what he is trying to say is the following. You see, first we will get what he is trying to say. And actually Brahmagupta in the Khandakadika, it is a Karana work, you see. So, for fast calculations without going to too much of theory. So, in that the sine tables are a very rough values are given, that is at the interval of 15 degrees. So, that is 900 minutes, that is why the 900 is coming. So, the that 90 degrees is divided into 6 portions. So, he is giving the values for the 6 these things. So, intermediate values how do you get? So, because these intervals are so large, so more better approximation for the intermediate values is needed. So, that is why he is saying this. So, what he is saying is following. Okay. Suppose one is given, in fact he does not say sine or cosine and all that, obviously it is for sine and cosine from the context, actually it is valid for any function and any function. Suppose you are given some function at the interval of alpha, you see. So, alpha, 2 alpha, 3 alpha, like that. Suppose you are given the values at I minus 1 stage is this, f of I minus 1 alpha, then f of I alpha, then f of I plus 1 alpha. So, then what he is saying is that suppose beta is a fraction. So, f of I alpha plus beta alpha is f of I alpha plus beta alpha by alpha is into delta of I plus 1 plus delta I by 2 plus beta into delta of I plus 1 minus delta I by 2. That is what he is saying. And what is delta I? That is the difference, you see, I alpha and I minus 1 alpha. So, that is the difference, and this is the next difference, you see. Indian Jya we are talking about, right, the difference between the signs at successive this thing values of this multiple stuff. So, that is that. So, you are taking these and then you find out, that is what he is saying. So, now compare with the Taylor series, the modern Taylor series. Of course, he does not talk about it, I am saying just to for comparison. If you take this, this is how you do your Taylor series in modern times. F of I alpha is suppose you know the function at this value, then to find this you have to know the derivatives of df at various orders, and first order this is this, and second order you have to have this kind of a term. The second order also it is called Newton-Stirling formula, second order this thing. And so, Brahmagupta is taking this, essentially he is taking df by dx as this. So, this is the change and this is the amount of change in the angle. So, this is the rate of change. So, he is taking the average of the rate of change at 2 points, I alpha and I plus 1, average rate of change at I plus 1 alpha and I alpha, and d squared f by dx is he is saying the difference between these. You see, these are rate of change at I plus 1 alpha, these are rate of change in I alpha. Essentially, it is related to the second derivative as we call it. So, it is very amazing that he is discussing this in 650 AD or whatever, that is what it is, right. So, only you have to plug in properly, as I told you, I mean what he says is this, but we can very clearly see that alpha is 900 minutes and all the other things, you see, half the difference of the tabular difference he is saying, all the things he is saying, and passed on the triple and divide by 900, all less or greater than the tabular difference. So, all the ingredients are there, and essentially he is giving this formula which we can understand like this. So, you can get more accurate values for the intermediate angle, that is what I am trying to say. So, that is the second order interpolation formula for which Brahmagupta is justly famous. Then apart from tables, one can do with find out exact values for the 24-hour signs without so Professor Ram Subramanian also was mentioning that. So, without doing the tables, one can find out all the 24-hour signs using a geometrical method. Okay, that is what he was saying. See, for instance, if you inscribe a hexagon, you can see that r sin 30 degrees is equal to r by 2. Okay. So, this is a hexagon, this side. So, this angle is 60, half angle is 30. So, this is r by 2, this is r by 2, this is r. So, sin 30 is r by 2 basically, sin 30 is r by 2. Similarly, sin 45 degrees is 1 by root 2, right. So that is also given in, these are explicitly stated in the works, various textbooks, books in Indian mathematics and astronomy. And so sin 30, sin 45, and if sin theta, you can find out cos theta from this. In particular, in the 24th division, if you know the ith r sin, that is r sin, it should be I alpha. We also know 24 minus ith r sin, that is r sin 24 minus I alpha, as 24 alpha is 90 degrees. So 24 minus I or 24 minus I alpha is r sin 90 minus I alpha, which is r cos I alpha, which is this. So what I am trying to say is, for instance, suppose I is 2, okay, then r sin 22 alpha essentially is square root of r squared minus this one, this one, right. So r sin 22 alpha is square root of r squared minus r squared sin squared 2 alpha. So from 2 you can find out 22, so like that. And it is realized that we can find r sin theta by 2 from r cos theta, which can be found from r sin theta. So in his Brahmasputa Siddhanta, Brahmagupta says, Utkrama Samakhanda Guna Vyasat Athava Chaturtha Bhagadyam Krutva Ukta Khandakani Jardhanenam Nalagvam Asmat. The square root of the fourth part of the verse sign of an arc multiplied by the diameter is the r sin of half the torque. That is what it means. So r sin theta by 2 is essentially, he is giving this d by 4 into this, so it is square root of r by 2 into r into 1 minus cos theta. So essentially he is saying to say the sin squared theta by 2 is equal to half of 1 minus cos theta. This we know, right. So this formula also was known. So in fact this is, it had been noticed earlier by Varahamihira himself. Varahamihira, who was just almost a contemporary of Aryabhatta, slightly later, Aryabhatiya 499 CE, and Varahamihira's Pancha Siddhantika was around 520 or something like that. So there he describes 5 systems of astronomy and so on, Pancha, that is why Pancha Siddhantika, and there he describes some trigonometry. So that is what he says, Ishtamsha Dvigunona Tribhajyayona Trayasya Chapajya Shashtiguna Sa Karani Taya Dhruvona Avasheshasya. So twice any desired arc is subtracted from 3 sines, that is 90 degrees. The r sin of the remainder is subtracted from the r sin of 3 sines. The result multiplied by 60 is the square of r sin of the torque. Okay. So that is the thing. See, I should mention that sometimes that capital R is not always taken to be 3438. Sometimes some other values also are taken for simplicity in calculation. So Varahamihira is taking capital R to be 120. So that is why he is saying 60 is coming in his verse, Shashti. So that is r by 2. Even Siddhanta Shiromani Bhaskara will take a shorter sign table, so he will take, because for faster computations he will take a r is equal to 120 there also. So like that, so it is only a constant here. So this is essentially, so this formula that you can find out, sorry I am wrong, here it must be 1 minus cos theta 2 theta, right, twice any desired r 2 theta, this is not correct, it is cos 2 theta. So essentially, so cos 2 theta is found from sin 2 theta. So if you know sin 2 theta, you can find sin theta, or if you know sin theta, you can find sin theta by 2. So essentially, so you know sin 30, you know sin 45, you know sin 90, sin theta by 2 from sin theta, and you know how to get sin 90 minus theta from sin theta. So using this one can construct it. So with the knowledge of the 8th sine, which is sin 30 degrees is equal to half, the 12th sine, which is sin 45 degrees is equal to 1 by root 2, I by 2th sine from ith sine, 24 minus ith sine from ith sine, one can find out the whole. So from 8 you can find out 16 8th sine, and from 8 you can get from the half sin theta by 2 formula you can get 4 and 20, from 4 you can get 2, I mean that second sine, 22nd sine. From 2 you can get first sine and 23rd sine. From 22 you can get 11 sine and 13 sine, you see. I mean this 13 means 22, sorry 11, 24 minus 11, right. From 20 you can get 10 and 14, from 10 you can get 5 and 19, like that, and from the 12th sine you can get this. So you can see that everything is covered. So all the 24 sines can be found using this method, and there will be lots of square roots on the way. So the method is exact but cumbersome. So like finding the circumference, inscribing polygons with larger and larger number of sides. One can keep on doing it, can get a large, very high accuracy, but it is very cumbersome after some time. You have to do lot of on this square root and square root of square root of square root, like that. Now Bhaskara Jyotpatti is called some 30 verses or so, or 28, I do not remember. So that is at the end of this so called Goladhyaya of Siddhanta Shiromani. So Siddhanta Shiromani and this spherical astronomy part, at the end is Jyotpatti he calls, So it is interesting, So what it means, a generation of science, okay. So that is the Indian way of this thing. You get the numbers, and of course with all accuracy and with all following all the logic, okay. But that is the important thing, and on the theory you can learn, that is do it later also. So for instance, he gives a method for finding sine 18 degrees in this. So 18 degrees does not come in this sine 24, you see, it does not come. So he gives a method. So he says Trijya Krutishu Ghatat Moolam Trijyonitam Chaturtha Bhaktam Ashtadasha Bhaganam Jiva Spashta Bhavatyevam. So deduct the radius from the square root of the product of the square of radius and 5 and divide the remainder by 4. The quotient thus found will be give the exact R sine of 18 degrees. So he is saying that R sine 18 degrees is equal to R into root 5 minus 1 by 4. Because he does not give the, in the Vasana he will explain the method. So essentially what is what one has to do is the following. So the circle of radius R. So here this AOB is 36 degrees. AOB is 36 degrees, of course. It looks much larger than that. For clarity, assume it is 36. Okay. Then OAB is 72. This angle is 72. This is 72. Also 72. And let this AD bisect this OB. So you are taking this angle, isosceles triangle. Okay, this is 36, this is 72, this is 72, this is radius, okay, and your angle OAD. So this is 72 by 2, so this is 36, so this is 36, this is 108, and this is 72, this is 72. So this is also an isosceles triangle. AD is equal to AB, and AD also equal to OD. Okay, it may not appear like that, I am sorry, the figure is not to scale. So from these things one can find out the sine 18. So for instance, OF bisects this angle AOB, and OF is perpendicular to AB. So AOF, that is 18 degrees. So now let x is equal to R sine 18. So your AB is equal to 2AF, and AF is R sine 18. So you call it as 2x. So one can see that, one can show that ABD, the triangle ABD and OAB, they are similar. One can show that because both of them 72, 72. No. But ABD, ABD. So this is 72, this is 72, this is 36. Similarly, OAB, this is 72, this is 72, this is 36. So they are similar. So you get AB by BD is equal to OA by AB. So AB squared is equal to OA into BD. So now BD is, this is BD is OB minus OD. So, it is r minus 2x and OA is r. So, essentially you get from this AB squared is equal to OA BD, that translates into 2x squared is equal to r into r minus 2x. So, finally you get x is equal, so this x sin 18 r sin 18. So, 4x squared plus 2rx minus r squared is equal to 0. So, this is a quadratic equation, so you get the solution. So, you will get root 5 minus 1 by 4. So, r sin 18 is equal to r into root 5 minus 1 by 4. So, this is a angle which he has discussed in detail. Similarly, in another verse he gives the r sin 36. So, tijjakrutishu ghatat tijjakruti varga panchaghatasya mulonat ashtahrutat moolam shat trimshadamshajya. Deduct the square root of 5 times the fourth power of the radius from 5 times the square of radius and divide the remainder by 8. The square root of the quotient will be the r sin of 36 degrees. So, using similar methods one can do. In fact, this is r sin 36, he is giving this is the thing 5 root of 5 and then inside the root there is another root. So, sin 36 is giving as, you take first find 5 minus root 5 by 8 and take the square root of that. So, this can be understood as follows, because sin 36 is equal to square root of half of 1 minus cos 72, okay, and cos 72 is sin 18 and sin 18 you have found, right, square root of half this thing 1 minus root 5 minus 1 this thing. So, finally you get this. So, this is the, so this is how he has of course, he has discussed more things in Jyotpatti. So, we will come to that later. For instance, he will tell how to find out, you found 24 r sines, then he will tell how to find out 30 r sines, that is, if you divide 90 into 30 divisions, then how to find, that is, find the sine at the interval of 3 degrees or sine of 1.5 degrees, and then he will go to sine of 1 degree, sine 1, sine 2, sine 3, etc., how to find. So, those things also he will do in Jyotpatti, so which he will do in the next lecture. In fact, he will say some very important things, important results of related to sine and cosine in the Jyotpatti. So, the famous, you all of know that sin A plus B is sin A cos B plus cos A sin B. So, those things he will discuss in that. So, next lecture we will start with this more things on Jyotpatti. So, the references are given here. Thank you.